Morning, everybody. Sorry for the late start, but technical difficulties right before I started. All right, so let's see. Administration. There really should be nobody in this room unless you are enrolled in the class, right? Because I gave the ads out, all that sort of stuff. This is the sheet that I have for attendance. It probably doesn't, those that were on the wait list and got added, they're not on here yet. That'll happen Monday. But I'm going to send this around, okay? Top half is the 8 a.m., second half is the, just put check mark, okay? On the days it filled out for the last 3 days. That's basically how I take roll in here. Homework is due not this weekend, but please don't ignore it, right? After today, to really start getting into it. And when do you need to have all of your technical support problems answered? This week. ID, yeah, by yesterday. Hopefully by this Friday, right? Come into grasp. We'll try to sort out whatever widely issues you have and that kind of thing. I don't remember who it was who asked me, but I put a folder that's got the blank PDFs. Okay, I put out an announcement. It's on the course modules, right? So you can go in there and pull up the blanks. We'll see how that goes. It took me a while this morning. Not because I'm inept, but just because my workflow is complicated. So it won't be every slide because there are some tricks that I need to hide, right? But I'll do my best to try and have those too. I need feedback on that. Yeah. What? Yeah, all the days that you've been here or not. So yeah, let me know if that's working for you, if they could be better, if they could be worse, whatever, right? I need feedback. If I don't hear anything, I might stop doing it, right? So let me know. Let's see, what are we doing? Chapter 21. That's right. You are going to hear a lot about Michael Faraday this semester. As far as old white guys go, he's pretty good on a lot of different levels. And I think you're going to relate in a lot of ways to his life. But right now is not a time for his life story. We'll get into that later. Just know that he is one of us. When it comes to the geniuses and giants of scientific history and the people that really kind of move forward our understanding of how the universe works, we often, think of the Newtons and the Einsteins, and they're these unapproachable geniuses. In the case of Newton, he was a jerk. Einstein wasn't a jerk so much as he just kind of didn't have the social graces. Michael Faraday was born poor, and through incredible trial in his life became what he was. He's the story of how hard work can get you places. What we are going to study, the nature of charge, how charges function, Coulomb's law, the electric field, most of our modern understanding of it is because of him. And we're going to hear over and over about it, but I wanted you to know that because he's one of my favorite people ever. And I'll talk about him a lot. I want you to turn to each other and brainstorm or list in like a minute and a half everything you know about charge. Charges, whatever. Go. All right. What did you come up with? Either based on your reading or what you knew. What is charge? What do you know about it? Oh, it comes in two flavors. Positive and negative. Vanilla and chocolate. Strawberry and cream. They're labels, but there's two kinds. Right? Okay, what else do you know? They have to be balanced. That sounds like a chemist. If something has no charge, is that true? Like the desk right here is neutral, right? Okay. Does that mean it doesn't have any charge in it? No, it has charge, right? It's just that those charges are balanced. An equal number of positive and negative in this desk to overall become neutral. Okay. So from that statement, what do we learn about charge? Everything has charge. So charge is universal. There is one thing in this universe that doesn't have charge and doesn't have mass. What is it? Light. Okay, right? I'm oversimplifying here a little bit, but light. Everything else has mass and charge. Okay? So you can take those to the bank, right? So it's a universal thing. And guaranteed, if it's got mass, it's got charge. Okay? So what else? So we learned it's universal. We learned that, meaning it's everywhere, right? We know it comes in two flavors. We know that in order for something to be neutral, we have to balance the amount of charge. So they're like canceling each other out or something like that. What else do we know? Opposites attract and likes repel. Attraction and repulsion is pushing and pulling, isn't it? And that's a force.
It's dictated by the number of protons and electrons.
Okay. You just brought up protons and electrons. We're going to talk a lot about that, but not right now. So if you want to go around believing in protons and electrons, that's fine. Okay? But physicists do that when we do quantum mechanics. Okay? Because, as you'll see, chasing electrons around can be a problem. We choose instead to think of charge in things as more like a fluid or water. This is a very classical approach to it. My desk has a ocean, a sea of charges in it. It just happens to be equal on both sides, so it's all neutral, right? But if something gets charged up, I'm not going to say I put electrons on it. I'm not. Just real quick, what's the problem with electrons and protons? No. No. They're real. That's the problem. Okay? No, that was a joke. The problem with electrons is that they're negative. How many times do you ever make a minus sign here chasing an electron around? All the time. What's the problem with protons? They're stuck. So when something is positively charged, what happened? Electrons left. That's harder than just saying it got positive charge on it or got negative charge on it. So the charged model of matter is actually the one that everybody uses whether you think about it or not. It's really kind of only the chemists and the quantum mechanics to start getting into the weeds. Okay, so we know it's universal. We know there's two kinds. We know that forces are involved, right? And the more you have of the imbalance, the stronger those forces might be. So the nature of charge was actually understood well after the nature of magnetism, but we do start with charge in the modern sort of concept of electricity and magnetism. But what we need to do is we need to kind of understand the relation between all of these ideas. And so in science, what's the way that we try to understand the relationships between things? We write down equations, right? Okay, but before we get to the equations, let's do just a little bit more concept, okay? Make sure we understand the nature of charge. This is a rubber rod, okay? This is one too many cats that peed in my kid's sandbox. No. This is responsibly obtained and harvested rabbit fur, okay? But I need the fur and I need the plastic in order to demonstrate nature of charge, okay? What I've got up here at the front is this thing called an electroscope. It consists of so the round circle is just a support structure. It's not doing anything. There is a plastic insulator right here that is preventing the charge from moving through, except this disc on top is connected with metal, with a conductor, all the way down this middle support right here. So electrically, the top is connected to this middle, which is also electrically connected to this needle. Okay? You can see the needle can very easily move out of position with very slight force applied to it. So the electroscope, the electroscopes are designed to detect the presence of charges. So I'm going to take my rubber rod, I'm going to take my rabbit fur, and I'm going to rub them together. Mechanical to electrical. Right? What happened to the needle? Oh, it moved. It deflected, right? Okay. So my action of rubbing the rubber rod with the rabbit fur caused a polarization, an imbalance of charge, because they start off neutral, right? The electroscope was neutral. The needle wasn't doing anything. But now there's an excess of some kind of charge on there, and I know it's an excess because the needle's deflecting, and all those charges, they don't want to be near each other, right? If they're all the same sign, they likes repel, right? They get as far away from each other as possible. So the needle is going to deflect. So that was the rabbit fur and the rubber rod. Now I have a glass rod and a piece of silk. Okay? I'm going to do the same thing. I'm going to rub the glass rod with the silk, and then I'm going to touch it to the electroscope. Ooh. What happened there? It got less, didn't it? In other words, it's not quite neutral, is it? But it's certainly, the needle's deflected less than it was before. What happened? I rubbed fur on a rubber rod and I charged up the electroscope, right? Okay, the electroscope needle went. And then I did the same thing with the glass and the silk, but then the needle went down when I touched it. Okay, wait. Let's ground it, neutralizing it. I'm a good source of like excess charge to get that needle back to, okay, there we go. So now I'm going to start with the glass rod and the silk. This is science. We should predict what's going to happen, right? Okay. What do you think is going to happen? Is the needle going to move or not? Yes? No? It moved. And it looked like it might have deflected almost as much as the rubber one, right? The glass one actually needs a little bit more. It's harder to get this one to charge. Okay, but look, it's deflected, right? So whatever charge is on here, it's all the same when I do the rubbing, and then it deflects, right? But now, if I take my plastic rod with the fur and I do this, what do you predict is going to happen? Is the needle going to deflect more or less? Less? Why?
Because there's an excess of negative charge right now, and you're about to.
I haven't said anything about negative and positive. But I come in here and I do this right. I did it wrong. This one, the rubber tends to have a lot of charge on it. Yeah, see, I've already, I dumped so much on there that I polarized it more. Okay? Sorry for my ineptitude, but it is kind of dry in here right now. These two rods have opposite charges on them. There are two different kinds of charge. Both of them can make the electroscope go up, but when I apply the opposite one, it goes down. And so the conclusion that scientists made was, well, there must be two kinds. So what do we call that? Positive and negative? Okay, right? Which is which? Which one of these is positive and which one of them is negative? They're not the same, they're opposites.
Rubber is more negatively charged because it's an insulator.
Glass is an insulator too. Yeah, Ben Franklin didn't know either. But guess who's responsible for choosing? Ben Franklin. It's a good guess though, right? Okay. Ben Franklin was really the first to kind of publish and really kind of nail down this idea. And if I'm correct, I never write this down in my notes and I'm dyslexic, so I could get this backwards, right? Okay. He defined the rubber rod as being positive. He just said it. This is positive, which automatically makes this one negative. What Ben Franklin didn't know is that he got it wrong. Because based on that choice, 150 years later, the electron, when it would become discovered, would end up being what? Negatively charged. Why is that a problem? Because multiple times in this class, you're going to do a problem, and it's going to take you 3 to 4 hours, and you're going to get to the end, and you're going to, with joy, happiness, and the hope of a youthful mind that cannot be stopped, put your answer into Wiley Plus, knowing full well you got it right, and it's going to come back wrong. And then you're going to go in and you're going to put a minus sign on, and it's going to turn green. And you will sit there, and you will want to take my name in vain, and you want to curse the day that you ever became an engineering major, or whatever. The person you need to blame is Ben Franklin. Because this would have been so much easier if electrons were positive. And they're not! And I'm hurt. You'll see, you'll see. You're going to experience, everybody experiences. Everybody. The chemists tend to ignore it, but everybody else has to deal with it. It's terrible. So, let me show you something else. Physics. I'm not touching you. I'm not touching the top, but the needle is moving. And then if I take it, oh, not quite. I transferred some charge. I must have gotten too close. What? What just happened? Sorcery, magic, action at a distance. What just happened? Why did that needle deflect even though I didn't touch it and didn't transfer any charge?
Electromagnetic field.
We'll get there. We're not there yet. What happened to the charges? Are there charges in the electroscope? How much charge do we have here? It's neutral. There is zero net charge. However, when I hold the positively charged rubber rod up there, okay, what happens to the negative charges in the electroscope? What do they want to do? Opposites attract, right? So the negative charges move up towards the positively charged rod. They can't get there, there's a gap, but they all pile up on this top disc. And what does that leave behind? A bunch of positive charge. And what do positive charges not want to do? Be together. And so they'll pile on that needle and push it away. That's polarization, right? I polarize. It's still neutral. It's just I caused a separation of the positive and negative charges. And then that needle showed that. Charge is tricky. And we're going to be spending a lot of our time in here chasing it around. So, let's see how you're doing with understanding what we just talked about by doing a quiz. Now, I got to teach you how quizzes work in here. So this quiz, even though it's about charge, everybody takes 3 of these. Even though this quiz is about charge, this is more about how to take quizzes in here. So everybody gets 3. And then you guys can send anything we get back.
On the attendance sheet, you have 12 worksheets, 15. Were we supposed to check off the other ones?
Yeah.
Oh,
How would I not? I don't like it. No, I hear this guy. Yeah, somebody else's name is on there. There's a rough job this week. Where is the roll sheet? So apparently it's wrong on lots of different levels. So I'll just take it back and I'll get the rest of them together. Yeah, I have to, apparently we started on the 12th. Alright. Let's see, does anybody have 3 quizzes? You have more than
I'm back in spring. I'm like, there's only 2 choices.
Quizzes in here are an excuse to teach each other. As you'll see in a second, the points aren't going to matter all that much. So, how does this work? Let me pull up this. So, all right. So, notice that there's 2 quiz numbers up at the top there, right? 21.2 and 21.1 and 21.2. I usually code them as chapter number dot quiz number, right? So this is the first quiz in chapter 21, it'll be 21.1. But notice that there's 2 of them, right? And they're 3 points each. So what you're going to do on your quiz sheet is you're not going to forget to put your name on it because that's kind of important, okay? And I got the wrong numbers up here, but you're going to write down 21.1 and 21.2. And you're going to do 21.1 in like the first box. And then the next kind of row box down, you're going to do 21.2. Okay? And instead of out of 2 points, you're going to put down out of 3 points. Right? Yeah, for both, right? So on the quiz sheet, right? 21.1, 21.2, and then out of 3 for both of them. This is the slide I used for 4A. So notice that you've got 2 boxes there for putting answers. The reason, and so I'm going to give you a quiz question. And the question for 21.1 and the question for 21.2 are the same question, identical questions. The only difference between the two quizzes is that the first one, I'm going to have you do by yourself. No input from anybody else. You and the question. Why? Have you ever been in a situation like in a class? The teacher asks a question. People are thinking, you're like, oh yeah, no, okay, wait a second. I can get this. I can get this. And then the person next to you just blurts the answer out. What happens to like your your train of thought? What happens? Totally derailed, right? Because you hear the answer and your brain just jumps right to the answer, and you've just been denied a learning moment. And a learning moment is when this synapse and neuron connects to that one through the chain. If that chain isn't made, you're not making any progress. And so I want you to have a moment on your own to find out if you can do it. If you can't, fantastic. Now you know you can't do it, and now you know you got to figure it out, right? There's some work you've got to do. If you get it, fantastic too. But the point is, you should be trying it on your own. No help from anybody else. The second quiz, I'm going to have you turn to each other, share the answer that you got, and why. That's the key part right there. Because in that why, you are going to be teaching each other. And maybe you don't know, right? Maybe you're like, I'm totally lost. Please help me, right? And somebody can teach you. Or maybe both of you coming together will figure out, oh, maybe there's a third answer, or we each forgot something, or whatever, right? You'll have an opportunity to discuss it and update your answer. That's what the second box is for. The first box, when I call time, set in stone. Don't change that one. But the second box, you're going to be able to make updates and changes to your previous answer. You really need to have two answers because there's two quizzes. If your answer is identical between the two, just draw an arrow connecting the boxes. I'll know that means that it's the same. You don't have to rewrite everything, okay? If you make a change, you can just say, new answer this and why. Like why you made the change. I forgot about this thing, or I realized that I made a mistake, whatever, right? Just show some reason why you're changing your answer in the second box, okay? It doesn't have to be a rehash, right, of everything. At the end of the semester, I am going to collect these, and you're not going to get them back. So if you want a copy, make sure to be taking pictures or whatever it is you want to do with them. You can write everything down in your notes and just put the answers on here. I will check these to make sure that there's enough information there that shows me that you were here, okay? And then give you credit. But that's how this is going to flow. Like I said, first box is going to be on your own, and you got to give a reason. This is a terrible reason. Okay, I don't want to ever see this answer on anything. Okay? If you make changes, you will give the correct answer, okay, or whatever changes you make. But if it's the same, what are you going to do? Just draw an arrow. Okay? All right. And then, when we're all done, and I often forget to remind you, you are going to score yourself. You grade you. Often the hardest grader in the room. Okay? But some of you are like, sweet, 50 points. 50 out of 2. I'm done with quizzes, right? It's not about the point. You put points on it because students will ignore it if you don't, right? Okay? But I'm giving out about 150 points throughout the course of the semester. You need 50 to get an A. Once you get 50, we're done, okay, as far as your score is concerned. But by then, you're halfway through the semester, and you realize this is a wonderful opportunity and exercise to figure out what you know and what you don't know. It becomes reflexive at some point, okay? So you'll be surprised. You'll be surprised when you get your 50 points. Okay, so with all that in mind, let's try this method. I'm going to put a question up on the screen, and you guys are going to give me the answer, okay? But you're going to do it by yourself, with no help from anybody else, no looking at each other, right? Okay? But yeah, you're just going to try it yourself, all right? And then I'll call time, and I'll tell you when to turn to each other. Now that you've had a chance to kind of read it, and I know you're not really understanding what I'm asking, but let me try to explain. For the sake of keeping everybody on the same page, let's say that the cat is negatively charged. Okay? Slides down the rod, becomes negatively charged. Okay? So that way we're just all operating with the same starting information. Okay? Right? So the cat's going to slide down the rod. It's going to let go of the rod, and then it's going to fall into the conducting pail A. What I need you to do is tell me what the charge is on pail A. And then the shelf is going to break. And I want to know what the charges are going to be on pails B and C. Everybody understand? Key things. Pails are metal, they're conductors. The shelf and the floor are insulators. See if you can't figure out what the charges are on A, B, and C. A and B, sorry. A and B. And C if you want. Once you get B, you know C. About 30 seconds more. I know some of you are sitting there going, oh, I have no idea what's going on. That's okay. You're going to figure out where do you need to start. But try to have an answer. I'll give you a clue, right? The pail either has to be positively or negatively charged, right? Those are your choices. Okay. At this point, hopefully you have something down in your box, right? 2 answers, one for pail A, one for pail B, right? Positive or negative. At this point, you're not going to change anything in that box. Set in stone. I want you to turn to each other, tell them what your answers are and why. Go!
Because all the bills are still negative. B next to it, it's gonna be positive. And the only reason why,
All right, keep talking, but make sure if you've changed your answer to make that change on the quiz sheet, right?
because for me,
If you keep it the same, what are you going to do? Draw an arrow, right? But if you're making any changes, make the change and why. Why you change it. What convinced you? All that kind of stuff. You are not required to answer the same as your group. The group quiz just means that you had input, right? You talked with somebody else, right? But if you still want to stick with your original answer, you do that. You do not have to answer the same as the people around you, right? It's still your individual answer. It's just that it had group input associated with it. Okay? Just to point out, I got it exactly backwards. Plastic rods are negative, according to Ben Franklin. But it doesn't matter. We'll stick with our negative cat here, okay? So, what is the charge on pail A? Positive or negative?
Negative.
Okay, why is the pail A negative?
it's negative charge.
A negatively charged object touched the pail, right? Just like my electroscope, right? Touch it, transfer of charge, direct transfer of charge. What's the difference between an insulator and a conductor?
Conductor allows the charges
To move through it. Yeah, that's it, right? A conductor allows charges to move through it, whereas an insulator, you can charge insulators. I just did it, right? I rubbed rubber, okay? But the charge piles up and can't move around, either on or through the insulator, okay? So the fact that we have an insulating shelf and an insulating floor means that there is no direct electrical connection between pail A and pail B, right? What about B and C? Are they electrically connected?
Yeah.
They're touching each other, right? They're both conductors in contact. So any charge, like if the cat fell into pail B, what would pail C end up being? Also negative. They're touching each other. It's like they're one conductor, okay? And that negative charge is going to get dumped on B, and then it's going to spread through both of them, right? Because the negative charges want to spread out and get as far away from each other as possible on that conductor. That's not what happens. Cat comes down, hits pail A becomes negatively charged. Shelf breaks, so when the pail A hits the floor, what's its charge? Still negative. There's no opportunity for that negative charge to go anywhere, right? Okay, the floor is an insulator, so the charge isn't going to go in, right? So are we okay that pail A stays negative? Starts negative, ends negative. Okay. So what is the charge on pail B? Positive or negative? That was a little bit less certain. Okay, by show of, let's maintain the illusion of democracy by voting. How many of you say that the pail is positive? How many of you say the pail is negative? How many of you are not voting? Thank you for being honest. All right? It's one or the other. What happens to pail A? Well, we know pail A becomes negatively charged, right? Think of this as one pail for right now because they're touching, right? What happened when I held the rod above the electroscope? It induces a charge. It causes a polarization to happen. These are neutral right now, right? But do they have positive or negative charge in them? Yeah. So what is all this negative charge going to do over here? It's going to polarize. It's going to cause all the positive charge to want to pile up on that end, and all the negative charges want to be as far away as possible. And now the shelf breaks. Pails B and C separate. When pail B hits the ground, what is it? Positive. What's pail C when it hits the ground?
There's enough negative charge in A and C to keep B from moving to either one.
Well, moving would be if they came into contact with each other.
Okay.
But yeah, they don't come in contact because the floor is an insulator. It doesn't allow charges to move anywhere.
Okay.
So if B and C weren't touching and that happened, it would just remain neutral?
C would probably, they would both remain neutral, yeah. Yeah, after the shelf broke. It depends on how close A lands to B and C to maintain the polarization.
Why wouldn't they induce a charge on each other when they fall separated? Like if one
Because of
thing-
conservation of charge and energy. Oh, that's the other thing that we didn't fail to list. Charge is conserved. But we'll get there. All right. How you feeling? Confused? Did you walk into this room thinking you knew what charge was? Yeah, probably, right? And now, hopefully, you are a little bit less sure. I know that sounds weird, right? Why, Mr. Balogh, would you want me to come into and become less sure about something? Because now we're learning. And because, and I told my Physics 2A students this, I'm going to tell you guys because you never had me before. You need to realize something about either my teaching style or what we're up against in physics education. When you go to a philosophy class or a history class or something like that, right? You walk in with your knowledge bucket, okay? And generally, your knowledge bucket is empty. Oh, fill my knowledge bucket, right? You come into that class and the teacher just goes, starts pouring stuff into your knowledge bucket, right? With physics, you come into class with your knowledge bucket and it's already full. Not just because you took physics 4A, but because you've lived in the physical universe and you think you know how it works. As you found out in 4A, not everything is as it seems, right? And so you come in with your knowledge bucket and it's brimmed top to the full of water, knowledge, and unfortunately some of that water is dirty. So what do I have to do? I gotta dump your bucket, right? I gotta dump some of that bad water out and fill it back up with clean water. In other words, you come in with preconceived notions about charge, about mass, about how the universe works, and I stand up here and go, you're wrong. In the form of getting quizzes wrong or, asking you something, you're like, oh, I thought I was thinking the opposite or whatever, right? What I'm doing is I'm trying to put you in a situation where you are recognizing the misconception that you have or the intuition that you thought you had or something like that, and then giving you an opportunity to analyze, to change, to learn, to grow. That's really kind of why STEM classes are as hard as they are. It's because you're constantly failing, we're telling you wrong, and it's because you're coming with a lot of preconceived notions that say, political science in 14th century France, you're not going to know anything about it, right? So you're not a blank slate, is what I'm trying to say. So please don't take my yelling, my screaming, my anger, any of that stuff is directed towards you. I'm trying to I'm trying to empty your bucket, right? I'm giving you that jolt that causes some of that bad water to spill out so that we can get some good water back in. More old white guys. Charles Coulomb, okay, was the first to mathematically and experimentally try to put some sense to all these relationships we've been talking about, and he did it in something called Coulomb's law. And what Coulomb's law was a statement about the magnitude of the force between two charged objects. And I'm going to start with that symbol right there. I'm going to change it to an equal. So you can go ahead and write equals for now, but I'm just going to start here. Maybe just wait till I get this whole thing written down. You'll see what's going to go on. Okay? What Coulomb discovered is the product of the two charges. The symbol we use for charge is Q, little tiny q. We use positive Q sometimes, but little q for a little individual charge. The product, the multiplication between those, the amount of charge, had an influence on the force. More charges, more force. less magnitude of charge, less magnitude of force. So that's why there's a direct relationship there, right? But he also discovered that the further apart you put those charges, the less force you have. And as measurements were done, they discovered that the further away you got, like if you doubled the distance between the charges, the force did not go down by half, it went down by a quarter. And if you tripled the distance, it didn't go down by 3, it went down by 9. This is called an inverse square law, and you've encountered them before in Physics 4a, and in Physics 4c you counted quite a few, okay? But if you take two charges which have units, does anybody want to guess what the unit of charge is? The coulomb, okay? If you take a coulomb squared, capital C by the way, not little c speed of light, and you divide by a meter squared, you do not get a Newton. What's a Newton? Unit of force, right? Okay, we're going for a force here, aren't we? Okay, so to fix that, to make it an equal sign, too close. To make it an equal sign, you add a constant. In this case, the electric force constant, K sub E. So now we can do that. And you hope beyond hope that this constant is truly a constant, right? That no matter what arrangement of two charges and the distance between them and the force you measure, you always get the same number out. Well, that's exactly what happened. This constant was eventually measured to be 8.99 times 10 to the 9 Newton times a meter squared divided by Coulomb squared. That's what the units had to be in order for this all to come out in newtons. This is often shortened to 9 times 10 to the 9, right? Okay. You'll see me do that quite a bit, especially if I'm writing stuff down or even calculating my calculator. So don't be afraid to do that. But that isn't all. But wait, there's more. Force. Is it a vector, a scalar, or an elephant? It's a vector. So what on the other side is a vector? Charge isn't a vector. Charge is charge. Like saying mass is a vector. No. The attraction and repulsion? Where is that on the left-hand side? Nowhere. So we have to add something. We have to add a direction. But we don't want to change any of the magnitudes over there. So we need to add something with direction that has magnitude 1. A unit vector. What direction? X? Well, what about Y? What about Z? What about theta? What about phi? Which one haven't I named yet? Oh, it gets much worse. All right, what did I just write down? R hat. So what's the hat mean? It's a unit vector. This means it's a unit vector. It has magnitude 1, right? But what's the direction of R? I drop a positive charge on the board right there. Okay? And I take another positive charge and I stick it right here. What direction is the force on my test charge, my little one right here? This I'm gonna call this positive Q. This one will be little q. What's the direction of the force on little q? To the right. Right? How did you know this is right? Opposites repel, right? Okay. So what if I put little q up there? It's up. right? What if I put it down here? It's down. If I put it on the left-hand side? To the left. What if I put it up here? Ah, what'd you say? Away. Every single one of these vectors all point in the same direction. Away. If I have a negative charge on the board and I put a positive test charge right here, what direction is the force? It'll be towards it or inwards. Another way to say that, okay? But really, towards and away are the only two directions. All of these vectors are pointing in or towards the charge. All of these vectors are pointing away from the charge or outwards. By definition, positive r hat is away. The radial direction outwards from the origin is defined as the positive direction. And you want to get any guesses as to what towards is? Negative r hat. You've seen this before. You just didn't know it. Or maybe you did. I don't know how Dr. Kerfoot teaches this particular subject. But you've run into an inverse square law that involved the product of two things and a constant that also had a vector direction. What am I saying from Physics 4a? Gravitational force. The force due to gravity was equal to big G times 1 mass times 2 mass all over r squared. Did Dr. Kerfoot ever write down the vector form of it? Probably just this form, right? Because we all know which way gravity points. In. Gravity always points in. What direction is this? In. Because if I go to Antarctica, I can point in the same direction, even though their up is my down and vice versa, right? Gravity points in. So if we're going to write down the true vector force for Newton's universal law of gravitation, what do we have to add? A negative r hat. Gravity never points out. Gravity never pushes. It only pulls. That's what that negative r hat means. Electrical charge, on the other hand, even though it follows the same pattern, pushes and pulls. Electrical force, Coulomb's law, can pull in and it can push out. But I am nowhere done with blowing your mind. Here we go. Which of those two forces, the force between charges, a la Coulomb's law, or the gravitational force, is stronger? Coulomb's law? Put electron here, and then they're going to go together instead of get pulled down? Okay, gravity? All right. Let's do an experiment. Because the science, right? We do experiments to figure out just what the heck's going on. So the question is, which one's stronger? The gravitational force between masses or the electrical force between charges? So here's the experiment. We're going to go out here. We're going to go to the stairs out here, okay? And I'm going to start throwing you over the edge one at a time, right? We're going to give gravity a chance to act on you. When you hit the ground, I want to know which is stronger. The force of gravity pulling you down towards the center of the earth, or the electromagnetic repulsion between the charges in your body and the charges in the ground. Are you all ready to take that data? Yes. No, don't do that. Some of you are like, yeah, I'm doing it because it's better than this. Don't, no. Because which is stronger? The gravitational pull or the electromagnetic repulsion? Let's have a talk, okay? What happens if you go out there and jump? You die, right? Okay? You lose, and gravity loses. Because if gravity were stronger than the force of the ground pushing up on you, what would happen? You would keep going. Do you keep going? No. Coulomb's law, the force between charges, isn't an order of magnitude stronger. It's not 2 or 3 orders of magnitude stronger. It is 10 to the 29 times stronger than the force of gravity. Gravity is easy to overcome. You want to see me do it? You ready? This takes advanced training. You ready? Okay? Don't do this unless you have a master's degree. You ready?
Oh my goodness.
Okay? Thank you. Years of training and 2 degrees to get to that moment in my life. What did I just do? I jumped. Gravity was pulling on me which way? Down. But I pushed on the floor with more force than gravity was pulling me down. What force launched me into the air? What did you call it back in physics 4a when 2 objects were in contact with each other and the force was perpendicular to the surface? The normal force. What's the normal force?
When you're in equilibrium.
What is the normal force? It is Coulomb's law. It comes from the charges in the surface interacting with the charges in the other object. What is tension? Where does it come from? Not gravity. It's Coulomb's law. It's the charges pulling on each other. What's friction? It's Coulomb's law. Take your hand, both hands right now, put your fingers on the desk, and push your fingers into the desk. Push. Why do you feel the desk? Coulomb's law. Not gravity. When you sense anything with your fingers, with your lips, with your face, with your eyes, is that the gravitational force? No! What is it? It's electrical charges interacting with each other, which is Coulomb. That Coulomb's law was the fundamental force of physics 4a, and we never told you. Because you'd run screaming from the room if we started like this. And so we lied to you. We're the normal force. Your tension, your friction. Right? Oh, there's only 4 fundamental forces in the universe. Do you name them? Coulomb's law, gravity, strong and weak nuclear forces. Physics 4c, you cover strong and weak nuclear forces probably in like 20 minutes on one day because they're, okay? Almost everything you experience from moment to moment comes about because of the electrical charges interacting in certain ways. The only time you experience your gravity is through your mass and weight and that interaction. Which is, again, constant. But when you think of accelerating your car, why does your car go forward? Because there's friction. That's Coulomb's law. Did you realize that before you came in? Yeah, some of you, but most of you know. Congratulations, you are now a different person. You're going to walk out of this room different because now you know. It's a little bit of an exaggeration to say it's all Coulomb's law. This is the fundamental law that governs the force between 2 charges, right? But when you are interacting on this scale, there's the quintillions of charges interacting, right? And we got to get from 2 to quintillions. And we're going to do that in 2 weeks, okay? So we're going to start very slowly, baby steps, working our way from 2 to 3 to 10 to quintillions. You want to guess where the integral comes in? Yeah, the quintillion, right? Okay, right? And we don't want to keep adding stuff up manually, right? So it's coming, right? But I can't stress enough how big G. What's this number? This number's like something 6.67 times 10 to the minus 11? That's stupidly weak. Why do we think gravity is so strong? Because we live next to a planet that has a mass that's measured in the 10 to the 24 kilograms, right? We got a lot of mass here. Put two small masses a meter apart, gravity might as well not exist. The electric force law is going to win every time. All right, let me say this. This is not the way I use Coulomb's law. It's true. I wrote down the right thing. But I am now going to start expanding your knowledge beyond the book. Because the book doesn't do this. But all physicists do this. Okay? And so I'm going to show you the better way. You might think that it's worse on first glance because it'll be new to you. See, the thing is that you know how to work with vectors in physics 4a and stuff like that by like you do triangle this and component that and your book does all that. It's fine. Okay, do it that way. You can keep doing it that way. I don't. It doesn't matter to me. But let me show you the power of the r hat vector, because this is a power that we're going to absolutely need when we get to magnetism. And so one of the things that Mr. Balogh does, and the other physics teachers I've never really seen do this, is I tend to front load here in this. I could kind of easily skip over this part and then slam you with it halfway through the semester. Okay? I would rather expose you to this method right now of working with vectors and have you flounder a little bit so that by the time we get to magnetism, where it's like really hard, you have experience working with this method. And I'll explain kind of the differences in the. They're really the same. It's just kind of two mathematical approaches to the same thing. Because what we need to do is if we want to figure out, say, like what's the interaction in that charge and that charge, well, that's kind of all in a line, right? But what if there's 3, 4, 5, 6? What we have to do is we have to add up the vector sum of all the charges.
Electricity attracts when it acts between charges of different signs. But acting between charges that are the same, it repels. According to Coulomb's law,
the force two charges exert on a third is the vector sum of the forces each alone would exert. In fact, the forces from any number of positive charges and negative charges add together as vectors. So the total force is still calculated from Coulomb's law. Notice that positive charges are shown in red and negative charges are shown in blue.
What just happened? Did you catch the three-dimensional nature of kind of those vectors in space, right? What you just saw was a force field. Not the one you think you have in your head right now, like Star Trek, okay? But a true force field. A pattern of vectors that exists around a distribution, in this case, of charge. There's a gravitational field, which is also a force field. It's the distribution of gravity vectors, say around the Earth or the Moon or something like that, right? But a field is a collection of vectors, okay, trying to describe what's going on. So we have a force field here, and we're trying to use, I don't know why they didn't put a vector sign on this, it always bothered me. What's this trying to say? The total force is going to be the addition, the sum of all of the individual charges of QIs acting on the test charge, right, the one that they were wandering around with, right, and the distance squared and some direction, right? So what we're up against is how do we do that? How do we pull that off for distributions of charge? Okay? So I want to get started on that, and I'm not going to have time to finish that. But we'll get a good start on it. Okay. That. All right. Do you remember any of these? Some of it yesterday. Right? Okay. So I want to demonstrate this. I want to point something out. The better method of thinking about r hat vector. Coulomb's law, right? Q1, Q2 over r squared, r hat thing. A unit vector, as some of you discovered yesterday, can be found by doing what? You can take the actual vector and divide by what? Its magnitude. Right? So by definition, r hat, whatever that is, right? Points away, points towards, has magnitude 1, is going to be r vector, whatever the heck that is, divided by the length of r vector. R vector in physics always points from the thing that is causing the force or the field or whatever to the point where you're trying to measure that force or field. R vector starts on the thing causing and ends at the point where you're trying to measure. For this charge right here, where does R vector start? At this charge. This is the thing that's causing the force, right? This is the thing feeling the force. So R vector's length would be the distance from this charge to this charge, and its direction would be along the positive x-axis. What would this one be? Same. Starts on this big positive charge, ends on my test charge, would point along the positive y-axis. That's what R vector is. The thing they don't tell you in the book is that with r hat, you still need to go find r vector and the magnitude of r. They just never really say it that way. I don't know why. Because you can just see it. Literally, you can draw it on the diagram. It starts here, it ends here. If I can measure how long it is, I know its angle, I can find its components, and away I go. Right? So even though books tend to insist on only using this r hat notation, it usually leaves students, like all of a sudden it goes from r hat to sines and cosines, and students are like, what just happened? Well, what happened is there's really an r vector in there that we got to find and then find its magnitude. And it's often easier to find r vector and then its magnitude to find r hat than any other method that's out there. So this allows us then to substitute in, right? This r hat, which would then make Coulomb's law look like this. And there's a little bit of panic that sets in here. Because now it looks like Coulomb's law is an inverse cube law. It's not. It's still an inverse square. It's just that I wrote it in terms of an r vector instead of an r hat. Right? And because there was that extra magnitude of r, it gets put in there. It still turns out to be inverse square. But mathematically, I can write that, and this thing in the box tends to be the more useful form of Coulomb's law. And useful in the terms of like actually applying it to situations where there are pieces of charge, like this one. On this screen, I put down some positive charges and some negative charges, okay? So before we go here, let's just draw in the r vectors. The blue one is negative, the red ones are positive, okay? Let's talk about, and there's a notation that your book, I will use the same notation your book uses for subscripts. if I write the R1, 2 vector, that is the vector that starts on 1 and ends on 2. We're going to try and find the force on all these charges. Actually, probably just charge 3, okay, on Monday. But what would the R vector that starts on charge 1 and ends on charge look like? Where do I draw it? I draw it straight up, starting where? On 1, and it ends on 2. So the R1, 2 vector is right there. In fact, it is A. Do you see how that length is A right there? It is A j hat. Put a positive sign on it. Where'd the j hat come from? It's the y-axis, right? Positive j direction. Okay. All right. What does R1, 3 look like? Starts at 1, goes to 3. What does R2, 3 look like? Where does R2, 3 start? Starts on 2, goes to 3, right? So here's R2, 3, R1, 3. Is that difficult? Seems pretty straightforward, right? If I can start on one and the other, just draw a vector between them. Okay. What's the length of R2, 3? It's A. See, it says right there, A. Okay. And what's the direction it points? Positive I hat. It's supposed to be an I. Okay. Because I hat is the x direction, positive x direction. Okay. So what is R1, 3? What is the actual vector? Positive A, and I'll say I hat, plus A positive J hat. R1, 3 is a triangle. That is A, and it goes to the right and up. I literally just wrote down the vector's components by looking at a picture. So what's the length of R1? What's the length of R1, 2? A. What's the length of R2, 3? A. What's the length of R1, 3? Square root of A squared plus A squared, which is the same as A times the square root of 2. Because it's 45, 45 right triangle. Right? So I was able to write down what the vectors were and their magnitudes. And now I can plug into Coulomb's law and go. So this weekend, if you're getting started on the chapter 21 homework, which I do suggest you do, and you're going to be lost, it's going to be fine. Okay? But just like start getting into it and get into the weeds and see what you're up against. If you're ever struggling to figure out, like, R hat, what do I tell you? What's the R? Fall back on R vector. Draw your picture. Just a sketch. It doesn't even have to be like accurate, right? But just nail it to your diagram. Draw that vector and see where it takes you. It'll be easier to find R hat if you find R vector. And then it's magic. If I don't see you on Friday, I'll see you on Monday.